What I want to do now, today, is go through the law section that we did last time and recap what we did, and then launch ourselves into the force laws that are going to complement the entire theory. So this is all stuff that is being covered. We did the analogies. Oh, and I inserted this slide of a recap. So here's what I did. One of the problems of Newtonian mechanics is that there's just a lot of variables here and a lot of relationships, and everything seems, you kind of get used to it, but everything seems very discombobulated, and it's unclear what the overall structure is. And sometimes the whole thing actually looks circular. What is a law, and what's the definition, and what is this, and what is that? So I did it last time just by sketching it on the board, and I made this overview. I put it here with the list of variables we have, and I put this little overview here, and each chapter will see how we fill this little table in, right? So here we have our familiar variables, position, velocity. I added acceleration here. At this point, not that important. Momentum and force. We have our two analogs. The position is either a balance or a level of demand, the quantity you're demanding. And the momentum is the personal value you ascribe to something. So the intuition is the momentum is in the mass. The mass itself is the agent. So the price, if it's the analog to momentum, has to be in the agent, It's his or her price, okay? Not some market price, not something outside, not something anybody has to agree on necessarily, right? It's the personal value ascribed by the agent, okay? All right? And this is the force acting on the agent. Now, if it's acting on the agent, there's somebody who is incentivizing the agents is creating this want, right? So somebody wants something and can incentivize the agent. So the reaction force is then the agent force, okay? So this is also on the agent. This is inside the agent. In the impedance analogy, everything goes a little bit differently. And it's just, it's a little bit unfortunate that Max will have to take the analog to a mass to be an inductor. Had he taken a capacitor, everything would have been the same, but he did it, okay? So we think of a current, the velocity, the analog to velocity as an electrical current, not as a change in the magnetic flux, which would be the voltage. Now, because of that choice, everything turned around. Now, what's good about it is that it's just another way to write down all of Newtonian mechanics, because if you look at it, the whole thing is symmetrical, right? You have these two variables, and their time derivatives are these two, and then you have these two relationships, and you can flip one for the other. So it really doesn't matter what you do, okay? And electrical engineering, they took another approach, and you can take that also in economics, okay? So instead of saying that you have a balance, which is a level, you talk about the entire amount of acquisitions you did, which is more the feeling as a quantity you've got, right, in store. These are my total acquisitions. I'm pointing there, look at it, right, there they are. Huh? And then the quantity demand then feels like a flow, right? Huh? So you can also put the word flow here. So you're flowing in the goods, and you're creating this total amount of acquisitions that you may have in your cupboard door or whatever store you're using. All right, it's very different than this, where it's a balance in account. The balance level is high or low, and the number of acquisitions is big or small, large or small, I would say. All right? Huh? So then there's acceleration also has its two values, interpretations. And then instead of when you look at the one analog, when this one is a level, the other one is going to be some quantity, right? They pair up together. It's interesting how that works. So you have a flow, and it pairs up with a level. So if you're climbing a mountain, you're following the flow, that's your hiking path, and you're surmounting the different levels on the mountain. right? Huh? So you see this vector and this covector. So if this is your flow, then you can look at your level lines, and if you say this is the up direction, right? Huh? Then you can see how there's a pairing of this with a change in level like that, right? So when this is a level, that's the case here, then the velocity has to be a flow. The other way around, when this is a change in level, then this has to be a flow of value, okay? This is the natural pairing of two variables. Sometimes this is called a vector, and this is called a covector. This is in modern treatments. We never do it this way. In engineers, we are pretty primitive about it. We model a covector also as a vector, so we take some level lines, and then we find some orthogonal direction, and then we measure it, and we do this, and then we use the inner product to do it. But basically, it comes out to the same thing. This is a little bit less general because you may not have an inner product. You may not know what orthogonal is, right? And that's the typical case in economics. Anyway, that's in detail. But you see, it's interesting how this pairing goes. So here, you'll see these are levels, and there's a level of desirability. So I would say a desire is a flow, you know, and desirability is really a level. So this will be a voltage. Huh? This will be the magnetic flux. Huh? That's a level. Okay. This will be current, electrical current, and this will be the charge. Okay. So you have to be fluent in these two things. So you guys are talking about these bond graphs. These bond graphs all work in this analogy. All right? Huh? That also makes them a little bit confusing. And normal mechanical systems use this analogy, right? So, bond graph that came out of electrical engineering and uses this. The Laplace transform also tends to use this. So, it's all a little bit. So a voltage has a level, and a force has an intensity, right? The force is a flow. Okay. Strong or weak. Voltage are high or low. So you see, there's a different feeling. All right. Anyway, what we do is all of Newtonian mechanics comes down to, I believe, 4 equations. You can write the whole thing down. All right. So the first is what we call the definition of velocity. So we then take a position, we look at its time derivative at a certain point, and that's what we say is the velocity. Here we say, all right, what's the definition of the level of demand or the quantity demanded or the flow? Well, it's just I look at some kind of stock, some balance, and I see how the balance is changing over time. Okay? That's our definition. So this is the definition. This is another definition. Is we define the force as the rate of change of momentum, or the voltage as the rate of change. Electromotive force is as a rate of change of the magnetic flux. Okay, that's another definition. All right. But now you just have 2 differential equations, 2 first-order differential equations. What you're going to do with that? It just seems there are 2 separate things going on. Now, what's really going on is that they're being coupled. So this guy depends on the integral of that guy, and this guy depends on the integral of that guy. All right? Okay? So the force depends on the position. That's what the spring does, right? And the velocity depends on the momentum. That is what Newton's law does. The P as mv does, the definition of momentum does. Okay? So that's the extra thing we do. So we'll say that the velocity depends on the momentum. So this is actually 1 over m times v, right? So this is P is m times v. Okay? And this thing, you can say this is the spring law, right? Okay? Now this law can be something else. This force can come from somewhere else. This could also be a damping force. and then it actually doesn't depend on Q, then it depends on the velocity, all right? It could also be a constant, m times g, that's the gravitational force, right? Huh? It could be anything you like. This is the trick, huh? So this is all immutable, all right? Huh? So we kind of burn in that this has to be the case. You can drop this too, like in quantum mechanics or relativity, you drop this, huh? And you know, you have photons, they have no mass and all this. But for regular, these are all taken as true, right? You can drop this, but these two always remain true, okay? Huh? Sometimes you have to change the definition of time and space a little bit. But, okay. This one, but for us, is always true. And this one, we plug in anything we like. All right? Okay. This is the trick. So this is the whole structure. It's a set of coupled differential equations, first order differential equations. So that gives you second order, and this is the coupling. All right? Okay. Now, how do we do that in economic engineering? Well, we march our way through that the same way Newton did. And where did this go? And you'll see that the situation is a little weird. So he has a section called definition and another section laws. But this definition is definitely in the definition section. That's the definition of velocity. Okay, but this is what I would say is more of a law, right? Which is not always valid, by the way. Not all laws are always valid. And this is also in the definition section. So he saw this as a definition. Okay. We see that too as a definition. We call this the definition of momentum, but it really isn't the definition of momentum. But that was only seen later when they did relativity and quantum mechanics. This, in the definition section, he also defines the inertial force, which we will call the force of demand, right? Because inertia is demand, and force is force, so it's the force of demand. Huh? And this is what he calls the motive force, which we will call the economic motive force, right? Which is just an incentive or a desire or something like that. Okay? Huh? And he also defines those, but he doesn't tell us yet what they are. All right? Huh? In fact, he never gets around to this thing because he only worries about gravity, and then he really has this gravity that's inversely proportional, right? Inversely relative to the distance, the gravitational, I didn't even put it in this list, all right? Okay. But we as engineers, we're really interested in this guy and this guy, right? These are linear elements, you get linear models. Gravitation doesn't give you a linear model, all right? Huh? So we define the quantity demanded. We call the demand line, right? This is just the demand line or supply line, and we unified it in one. Okay. All right. Huh? Then we did these laws. So we talked about free motion as freedom from want. I guess what I want to keep stressing here is why did I use this freedom of want? Because presumably, if you can make this a principle that applies to the whole world, then it must be so that somebody can sit somewhere and close his eyes and not feel anything, and just ask himself, do I feel free from what? Okay? Huh? Okay? It should be the same way as you sit in a train or in your car. In a train is better because they go smoother than a car or an airplane. You don't look outside, you say, do I feel force-free? All right, that's all you need to do. Right? Do I feel any forces? And the answer should be yes, I can make that judgment. Can you? If so, yes, you do know how fast you're going. You say, well, I have no idea. Right? Huh? But you can determine whether you're force-free. Okay? Because you can feel the force without looking outside. All right? So what's important in this first law of Newton is that we say that although we cannot determine how much we're eating and breathing air or drinking water, without looking outside where it's coming from or something, we can determine that we're satisfied, that we don't need additional water or that we drink too much. Okay, by closing our eyes and not looking at the tap or the faucet or the well, or wherever you get your water from or your air from, right? Okay. Also, you don't need to look at what other people are getting, all right, to determine whether you are happy like this, okay? So things like jealousy and envy, you gotta get rid of that when you do that, because envy is a force, and it's more of a fictitious force that you see because somebody else is moving, right? But it cannot be part of this innate want, right? Because you have to look at somebody else to realize you're envious, all right? You see that point? So here the assumption is that it's an assumption we can make just by closing our eyes and not looking at our environment, just within ourselves. In the same way we can decide that we're going at a constant velocity, all right? Okay? All right. So this is important. And what we'll assume is that if we can do that, then there must exist some kind of frame, which we will call an inertial reference frame, with respect to which we can agree all to measure that. Because all of us could, at least conceptually, sit on top of this thing and go like, hey, I feel cool, right? I feel okay, all right? And this is important in engineering, all right? So that we have a point of calibration. So this is a point at which we're going to measure the quantity demanded, right? So if our quantity is higher than this, we'll call ourselves, I don't know, demanders, okay? And if it's lower, we'll call ourselves suppliers, or the other way around. I don't care, right? And when it's the same, we'll say we're neither. We're just in equilibrium with this environment, okay? So this is how we unify the two demand lines. Now, of course, you could have taken another constant here, 5. Okay, and what happens? All that happens is you shift over the whole demand line, right? P is in P graph. So every time you have a P, you have to just add 5. Now, you can do it that way. But that's not the way you do Newtonian mechanics, okay? You can do it that way, but we don't do it. And you don't do it in a bond graph either. You guys just did bond graphs and you say, well, where is the I element or the one junction where there is a zero velocity? Well, it isn't there because there's no power flowing in it, so they leave it out, right? Because if the velocity is 0, then the force times the velocity is always going to be 0, so there will be no net power flowing in or out. So it's there, but left out, okay? I just overheard you guys talking about these bond graphs, so I don't know. Okay? So this is important. But you see, because otherwise it just sounds trivial, this thing, right? It's like, okay, it's just a definition. No, it's not. It's really an assertion that something is the case in nature, or in this case in economics, that makes this possible, okay? And you just have to agree on that that's okay. All right? Okay, I'll buy this. I can really determine whether I'm free of any wants. Okay? Anyway. Then comes Newton's biggie. So, in the first law, he's already told you under what conditions there are no forces acting on you, okay? So, economically speaking, the first law tells us when we're free of wants, when we don't have any net desires, okay? But he hasn't told you yet what happens to you when you're not free of net desires, right? When there is a force acting on you, all right? And that's what Newton does in the second law, all right? So this law, he actually is intimately connected with the first law, because if this thing is 0, then you just get the first line, right? So they're really part of one law, all right? Okay? Now here he says that when, okay, I'll first say it mechanically. It says when a force acts on a particle, it increases the momentum of the particle, okay? Said in another way, the way Newton did it, he first defined what momentum was, and now he can, and then he defined what a force was, and then he makes the equality, okay? So in his definitions, he first says this thing, and he writes it like that, right, like a straight demand line. And then he says, well, this thing exists somewhere, and then he says this, okay? That's my law, okay? That's how he reasons. So if we do the same thing economically, we'll say first, we'll assume we'll have a linear demand line, all right? It's a unified, so it's also a supply line. Then we'll say, well, you know, we have this desire, okay, that we already know that when we're not demanding anything, that when our demand is uniform, this thing is zero, right? So, and now we have to think of what desire can be. Well, it should be something that is increasing the price, okay? It's a little cleaner to not assume this, okay? Just to say momentum is just a property of a thing. Just to say you have a price, okay? That's just your property, right? And if you desire something, you will raise your price for it, okay? And if you want to get rid of something, you will lower your price, okay? It's cleaner, I think. And that's how it's done in modern times. So in modern times, we don't assume this anymore. And there's a good reason, because if you have a photon has no mass, right? So what do you fit in here? You can't fit in zero. It has no mass, not zero mass. Because a photon does have momentum. And it has velocity, namely the speed of light, okay? Because it is light, but it has no mass. So this is not clean, right? So momentum is something way more elementary than this equation, okay? So it's just a property of something, okay? And that's how we want to view price. It's just a property of any person that he assigns his price to something, or endows it with a value, a personal value, all right? And that the agent of change of that value are his desires, okay, as I moved it, all right? That's the way you really want to think. So I love to think of this as a definition, right, in a more modern treatment, and it's also more logical, okay? Now, I want to keep emphasizing this is a brilliant move, okay? Because before Newton, people would use the word force all the time, but they would have no idea what it was. They just kind of know what works out, right? And they had the idea that they somehow had to balance the zero or something with y, okay? Well, only because you don't want this thing to start accelerating, okay? Because then there will be a net force. All right, that all follows from this law, okay? And the other thing, the problem they had is you can talk about a spring force being some value, but how do you know that it's the correct number? How do you know that the elastic force is this if you don't even know what that is? You have no way of calibrating it, okay? And how do you know that the damping force is this, or the gravitational force is this? How do you know all that? And then you can just compare these. You have no definition for force. There's no way you calibrate it. So the only way you really can calibrate it is to say, well, I have a mass of 1 kilogram, and I know that it's going with this, and then I can find out what the momentum is, and then I can, so I take a test mass, and then I can calculate what the acceleration is, and then Newton actually said this was proportional. And then people just said, well, take the proportionality constant to 1, and then you can calculate what the force is, and then you can calibrate the springs, your dampers, and all of that, you see? This is not how they teach it to you. They start off with statics, they're throwing a force at you, right? Now, you seem to have no problem with it, so that goes well. Then in strength of materials factor, they do the same thing. You know, then you even figure out how it's bending, you know, and still no problems. And then they finally do dynamics and they tell you that the net force causes an acceleration and a change of momentum, and then you get confused, right? Well, you thought you had no problems, but it's really the other way around. You shouldn't be confused all this while, real now. Okay? Anyway. But for economic engineering, it's good to see the structure clearly, right? So, what is the want or a desire or incentive or all these other things? If it's a force, it has to be a change in price for somebody, or at least it can exist, but it should be calibrated to a change in price. Okay. So you can build a system with only springs and dampers, but somebody somewhere has to have taken one of those springs or those dampers and calibrated it to a mass. Otherwise, the thing is meaningless. All right? And that's what you have to see here too. You can talk about all these economic forces, but somewhere back in your mind, you must realize that somebody has calibrated this thing against unit price elasticity or something. All right? You can also calibrate it onto a photon. You know, we'll get to the economic engineering equivalent of that, and then it's more of a wavelength kind of thing, you know, but you can calibrate it against anything you like. But as long as it's, well, not anything you like, as long as it's a momentum law, right? Okay? All right, is that clear? I like to hammer all this stuff in because it's really easy to slide and get it wrong, and then you get into a lot of trouble. All right? Okay? Now you see that Newton developed this notation, and you call it the Fluxion. So you can see that he thinks of momentum as a quantity. So price is not more as value, because the flux means a flow. So you can see that he thinks of a force as a flow of momentum, right? So he sees it flowing. That's exactly what we do. When you have a spring here, you can see the force flowing through there, in there. When you make a construction, you see these force lines in your mind, okay? That's not the picture that electrical engineers have. When they have an inductor, they don't see the force going through. They see the current going through, and then they see this thing more as a level change, you know? Okay? The voltage level. All right, spanningsverschil, we say. Voltage drop. Okay? So his notation, and electrical engineers don't use this notation, by the way. They'll write the voltage is d lambda et, where this is the magnetic flux. They don't use the dot notation. I've had renowned electrical engineers look at me and say, what does this dot mean? I just don't use it. It's Newton's thing, you know? Okay? So here's that other idea, right? So you get, instead of an bounce, you see a little level. Okay? So this is more of an idea that this price level gets accumulated by small price levels you integrate this. Right? Whatever. I don't want to go overboard on this either. Oh yeah, maybe here it's still, there was some confusion here last time. If you say that F is P naught like I did here, and you assume for the moment that it's just an elastic agent or an inelastic agent, right? Then you can plug that in, and then you know that this is M times A plus V times M dot, right? So the total force is this one plus that one, right? Okay? Usually we make this well. Usually economists do the same thing. They don't consider the price of electricity changing in time. Okay? There's another thing you can do, and that's when you're in trouble, when that reference frame that you don't have an inertial reference frame, right? So this reference frame also is an acceleration, okay? So it's moving away from you. So what happens is you get another force here, huh? Okay? I think I'm missing a minus sign here, huh? This plus shouldn't have been here, sorry, huh? Okay? All right, so there's an extra actual force. We call it a fictitious force, okay? So if you're sitting in your airplane and you're feeling good, and all of a sudden the airplane accelerates and you push back, right? Huh? Sometimes we call this the D'Alembert force, huh? All right? And it comes out of nowhere. And it's everywhere, for everybody at the same time. So nobody feels like you're pushing on you to do it. Right? Everybody gets pushed back in their chair. Right? It's a weird force. You see, this is actually an interesting thing, and you have to think in economics, like, of a force, we have a tendency to think that you need a point of application, right? You have this, and you're push on it. But some forces don't act that way. Like, a famous example is gravity. It's just everywhere. I don't care either point. This thing goes out, that thing, well, what up with it? I don't see anybody pulling, right? Huh? Okay? So is gravity the only force that is just everywhere? Now, which one do you think of? Huh?
Coriolis?
Yeah. Oh, this one. The D'Alembert force. I mean, if that plane is slowing down, everything on it gets pulled back by the same force. The Coriolis force is another one. There's another one, there's a third one. Huh? Centrifugal force. Right? Also comes out of nowhere, applies to all the clothes in your clothes dryer. At the same time, huh? Okay, huh? So nothing is pushing on it, right? Huh? So these forces are of a different nature than the applied force, you know? And they all have to do with the fact that you're not in an inertial reference frame, okay? That's what they have in common. They all have a minus sign. Okay? Huh? You see that? Huh? That's why Einstein figured out that gravity is a pseudo-force, right? Huh? It has to be because it goes also with a mass, with a minus sign, and it's everywhere. So it has to be like the D'Alembert force or the Coriolis force or one of those things. He had a little trouble working it out, but he succeeded, and it's true. Huh? It's because of some curvature, space-time, you know, that just shows up. Huh? Okay? Huh? So these forces, they're kind of interesting because they come out of nowhere, and you still feel them, but you wouldn't feel them in an inertial reference frame. So you have to look outside and see what's happening to your environment that you're making this error, that you're feeling that. So in order to properly explain these forces, you have to look outside the airplane and go, damn, this, you know, this thing is accelerating. Well, you have to look outside your car and go, like, hell, we're going a lot faster, right? Or your speedometer or whatever you do, okay? So these things are different, okay? So these forces, I would say, are more like forces of envy, you know? So you see, if this is your neighbor, and he is doing really well, and he's shooting off, you're starting to feel bad because you use him as your calibration point, you know? So suppose you're an investor and you're getting all your returns on your bonds and all this stuff is going really well, you know, and then you see the market taking off or some other investor doing much better, you're not feeling so good, right? Huh? I have this problem. I sit in an airplane and I got some really nice chair, and then I find out, I'm really pleased with myself, I find out that the guy sitting next to me is paid half the price. I immediately don't like my whole trip anymore, you know. Huh? But I shouldn't be concerned. If I had closed my eyes and not listened to him, I would have been okay, right? So they're real, these forces, but this is the feeling of the economic fictitious force. So it's more of an envy type of force. Huh? Okay. Yeah. All right. Huh? All right, then there is the last one. Look, really, the three laws is only one law. So how is this last one actually the reaction part of this? Look at what this thing says. It says that the force is the flow of value, right, or flow of momentum. Now, when is something a flow? Only when what goes out comes in somewhere else. Otherwise, it's not a flow, right? Huh? Okay? Huh? So this has to be some kind of conserved property. Otherwise, you couldn't take that time derivative, right? You understand? Huh? You can't depend on all of a sudden this thing taking a big jump or something. Huh? So this notation and this definition already implies that when you put a force on an item, huh? You know, so you're pouring this momentum in, it has to come out of you. You know? So there's this reaction force that exactly measures that. Okay? We just draw it, instead of a flow, where here is coming from here and entering there, we draw it as one force like this, and then the reaction force this way. Huh? It's a little bit confusing the way we draw it, but this is what happens here. Huh? If you use some really good differential geometry, this whole picture of the balancing of forces is that you have this, and you have this one, and this, all these things balance, and this means whatever is flowing in is flowing out. Right? So you got one point, the momentum flows in, and it has to flow out, otherwise it starts to accumulate momentum in it. All right? Huh? Okay? So it's kind of already built in this notation. So it's the same thing if you define the velocity as the change in position. It means if you're here and then you move to the right, from the perspective of this guy, you move to the left. I mean, if this was what was gained from the right, you know, this little piece here, then this must be what was lost going from the left, you see? So defining this way, the velocity also implies that space doesn't come out of nowhere, that the distance between the two walls is a constant, okay? If the walls are going out, then you can't define distance this way, all right? Huh? Velocity this way, okay? Now, this Newton formula, formalized with this is action equal reaction law, okay? I think that's the way he must have conceptualized it. Otherwise, how do you come up with this, okay? All right? So you have to think of a force as a flow of momentum. If we think of a force as a flow of value, the value has to come from somewhere and has to go somewhere. So what this means is that the way we should interpret that personal value, it gets created only in an exchange with another agent, okay? So what flows out from one has to flow into the other, because the momentum the value can only be stored in agents, okay? The momentum can only be stored in particles, so it has to flow from one to the other. You can have a big wall or a big market and dump it with a lot of value, and it probably won't move, change its movement very much. That's all fine, okay? You can have a wall and just dump all your momentum in there. Applied forces is not going to accelerate, okay? All right? Huh? But still, the value has to come from somewhere. The momentum has to come from somewhere. That makes the thing a conserved quantity, okay? If it's not conserved, everything is pointless, okay? So that's what this law says, okay? And you can see economists know that, at least implicitly, because when they draw these demand and supply graphs, if you go down here, and this is like a P dot, you know, then the change in price of this demander is going to be the opposite, you know, of the change in price for the supplier. Is that right? Yeah. Yeah, because this is plotted downwards, you know. Huh? Okay? All right? Huh? So this idea of marginal cost equaling marginal utility is another way of writing that you have a conservative value flow, right? So the marginal cost, that is a flow a little bit of the amount coming out from the supplier, and it has to decrease the. Huh? So we can also call this debit and a credit and things like that, whatever. Huh? Okay. And this type of value is what Smith calls value in exchange. So here he has this is a very famous paradox, showing that you have to be, if you think of price as value, you have to be careful what you mean by value, right? Huh? So you can't confuse it what Smith says with use value. So water has a lot of use value, and diamonds have no use value. I mean, they're pointless, okay? Most of the time, okay? You can make some tools out of it, maybe, or something, a very hard saw, okay? Huh? But when Smith uses value, or when we use value here, we must mean that it's value in exchange, okay? So it's value in use is something you can just look at yourself and determine what it is, okay? Well, I really need water, and I don't really care, well, that living in the desert doesn't need water, or a stone doesn't need water. What do I care, right? But that's not the right way to look at it. What you want to see is like, I need water, and somebody else also, who also needs water, happens to have a lot of it, so he's willing to partner this water and give it to me, and I give him something that he wants that I don't have, you see? So it's a value in exchange, not a value that you imagine, okay? And that's formalized by this third law, all right? But really, it's all part of one law, F is P law. The first law just says when P dot is zero, all right? So you're not changing your momentum, and the force must be zero, right? And then the second one says what happens when your momentum, your price does change, then there must be some desire that you have, okay? That is unfulfilled. And the third one says the way you should interpret this P is value in exchange, okay? It's the personal value you ascribe to it during the exchange that's going on. And the next exchange you may ascribe it another type of value, all right? So I buy this airplane ticket right now, it has this value to me. The second one is a lot less value because I can't sit in two chairs, huh? Okay?
But if I push a wall really hard, there is no momentum flow.
Yes, there is.
That will not change the velocity. My velocity doesn't change, and the velocity of the wall doesn't.
Very good question, and it has a very good answer. So this is a very good question, okay? I'm repeating myself, but there's a very good answer. So here's the wall and here's the ground, right? So they're attached, huh? Okay? And here is you, huh? Here's your feet. Huh? And you're pushing here, right? Okay? These are your feet. So this is a momentum flow, right? This is your force. Okay? It flows right back here. In your feet, through your feet. You have to anchor your feet, of course. Huh? Okay? And it just flows in a circle. So if I start leaning against this board like this, I can feel that, right? Mm-hmm. But nothing is moving. You know why? Because the momentum is just, and the harder I push, the bigger the circulation of momentum. Okay? Now that's what you feel. So you feel the momentum cycling through your body, and it's also cycling through the wall, but that's nothing is happening. That wall doesn't need to be a wall. You can take all the mass away and just sit there, huh? And connect yourself in this way. And you can pull your shoelaces and think that you're going up in the air, but you're not. The momentum is just circling around. Okay? Huh? And so it is with value. All right?
So if there is a force, there's always a flow in momentum.
That's right. Okay? So if there's a force going through a spring that's induced by a damper, then the flow of momentum goes like this, and here's another one, and it just circles around like that. Okay? All right? Because these walls are connected. If you have a beautiful cathedral, right, with these flying buttresses and all this stuff, right? Up. Now what happens? How does the momentum flow? Well, first of all, gravity pours it in, right? So in the roof and all the superstructure goes in, and then it has to flow to the ground, and then it gets poured in, and it's just flowing like that. That's why you try to make these cathedrals smooth like that, so that the momentum can flow really nicely. Otherwise, it's going to break because you get these force lines all piling up, and you can feel that they're going to. This is where it's going to be a high amount of pressure on that point. Huh? And what is this pressure? What is this stress? You feel these little stress down here. That's the density of the momentum lines. Okay. So if you do strength of materials, is exactly what you're looking at. Force as a. Huh? Okay. Huh? That's the right picture. So if you're a person and you're living in a society where there are some basic needs, we'll get to that, then those get poured into you all the time, okay? And somehow you have to keep standing on your own legs. We're going to get to that. So the picture is exactly the same. But it's always an interaction between two objects at every point, between the feet and this and this and this. Every point you can see what flows in has to flow out. The action has to equal the reaction, right? Okay? That's the correct way of looking at it. Otherwise, you get yourself confused over and over and over again. All right? That's the way they should have taught you this. I don't want to say that because they probably shouldn't have. But that's the picture Newton had. Otherwise, he wouldn't have been able to come up with this. Otherwise, it's all magic. Right? Huh? Okay? Did that convince you?
Yeah.
Yeah? Yeah, it's kind of magical because you realize it's sure I'm feeling that, right? There's a difference from this and this. So just because nothing is accelerating doesn't mean there's no momentum flowing.
No.
It's only
Yeah.
That's what I say. But you have to calibrate that force to one thing of which you can observe the change in motion, because we cannot observe momentum. We have no momentum monitor. We can't look at it and say, hey, there's momentum flowing, right? It's the same with the electric current. We can't see it flow. And in economics, it's the same with value. We can't say, hey, there's all this value flow, personal value flow. But we can see the goods flowing, right? So in mechanics, what we do is we look at the change of position, and then we take a special type of particle that is mass 1, or I don't know what you take, and then you start figuring out how much momentum you have. And we take some kind of standard consumer or something like that, and you figure out how much value is there. And then you can use that, for all your calculations, even when there is not a single consumer inside. We just have a bunch of storages and intermediaries, right? Okay? Okay, is that clear? So this is the magic way I feel that economic engineering is clear as out Newtonian mechanics, because almost every student is confused about this point. Okay? Even the best, like you. Now, it's a good question, and I thank you for asking it. Okay? Because I need some guts to ask these kind of questions. And they're really good questions. It's just not a good answer. Okay, so where does that bring us? That brings us here. This one and this one we already done, and we now did this one, right? A lot of work, okay? But it was worth it. This one kind of feels trivial. It's not so trivial, by the way. It just feels trivial. But Einstein had to fix this one, because they tried to fix this one, right? And it didn't work. This one is right. A lot of people still say that Newton was wrong. No, he wasn't. This is still valid. This is where the problems were. Okay? The definition of space and time. Okay? Not here. Still now I have people say, well, Newton was wrong. No, he wasn't. Huh? If you say that Newton said M times A, then he was wrong, because this A has got the wrong, is measured wrong, but he never said that. He said this. This is always truth. Okay? That's why I promoted her to a definition. Huh? And that's how we should do it too. Huh? Okay? So now, all that's left are these force laws, all right? Huh? And when we have that, then we're done. And we're not done, we're done with the foundations, and then we start developing concepts like energy, which is surplus, and equilibrium, and all of that, all right? But we need these 4 things, all right? So I want to do that in the remaining time, okay? You guys are all with me here? Any questions? Huh? It's a subtle business, but it's really worth your while to get fully to grasp, and it's very beautiful, I feel. It's very beautiful. It's a beautiful theory. So I'm going to start with a couple of force laws. So, see, this whole thing is pretty useless up to now, because you make 2 definitions, and then you've got this one little thing here, but then how do you use this for anything, right? You need this thing to somehow, you need to have some external forces or something to make this thing move, otherwise you just have a bunch of masses, I don't know, maybe you can do collisions with this or something, even then you can't do that, you're stuck. So we need this, all right? And the first thing, the simplest one we have is, I feel, is a constant force, okay? This is just an outside force, right? And what we'll say is, okay, we'll have some kind of agent, and its price change is a constant. Now, that sounds ridiculous, because that keeps, if that's a constant, then it'll keep upping its price, okay? I'll never ending, right? And if you think that sounds ridiculous, you're right, okay? And it also sounded ridiculous to everybody before Newton, right? So they couldn't imagine that if you took an object in a gravitational field, it will just keep going faster and faster. And it would make no sense to them. So there's another theory called Aristotelian mechanics that says that instead of accelerating at a constant rate, all objects would have a constant velocity, okay? And that's a little bit what you see, because if you drop something, there's going to be some terminal velocity, and then at some point, the object will start dropping at a constant rate, right? Huh? Now we would say, well, that is not really anything to do with the object. That is, well, it has to do with the object, but that's what happens when there's friction, right? So there's 2 things going on. There's gravity. Due to gravity, it's going to keep going on, and you got a quadratic taking off, right, of the position in time. But due to friction, you get this counterforce, and at some point, it will reach a terminal velocity. That's what we say now, but they didn't do that. So they had mechanics where, you had all these elements, some were lighter, like fire, and others were heavier, like water, and are really heavy, like Earth or something, and they're organized like that, right? And Kepler also had this idea that these planets were just, he couldn't see that the moon was falling, okay? That's what Newton said, the moon is falling. Did you know this? Huh? We should stick to economic engineering, but this is too good to pass up. So, this gravity comes from Newton's understanding of what it was. And they had 2 types of gravity, if you could call it that. So if you had a cannonball, they were interested in killing each other. But if you saw an apple fall, maybe we should use the apple. That's what Newton looked at, right? If you take an apple, this is not an apple. I can take somebody's Apple computer and drop it. Huh? Then if you let it fall, it's going to go straight down. Right? Huh? Now, if I give it an initial velocity, what is it going to do? Well, it won't go straight down. It will still go straight down, but it will kind of keep that velocity, right, due to the first law, and then make something that is linear here and quadratic this way, so it will be a parabola, right? Huh? And then we'll just hit the earth, right? So this is what you'll get. Here is your earth. Here is your apple, right? Huh? And then that no velocity will poof, right? Huh? And a little bit it will do this, and a little bit further it will do that, right? Huh? Now you have a situation where you have the earth here and then the moon there, and it turns around, right? Huh? Okay, now that looks totally different from this, right? Because this thing is not, the moon is not crashing against the earth, right? Huh? And this is what people said was falling, and this is what they would call celestial mechanics. So that was what they call terrestrial mechanics, huh? Terrestrial mechanics. So these were the cannonballs, and they figured out it was a parabola. And this was celestial mechanics, and Kepler figured out that this was an ellipse. All right? Huh? Okay. But they saw no connection. Do you see a connection? How can you get from like going straight down boink to never falling and still be falling? So Newton wrote an article and it said the moon is falling. So you could hear all the sages and crème la véritable intellectuelle of Europe laughing their heads on the moon. It's not falling. I mean, I don't see it falling. It doesn't fall forever. Huh? And they were wrong. The moon is falling. Okay? What he meant by that is this idea covers this too. Now, how do you see that? Right? And here's how you see that. Newton actually had a picture. He had a cannon up here. You know, it was shooting out these things, right? And he said, well, you know what you do? You put this on a really high mountain, and then you imagine that you shoot it out really, really hard, right? Now, the thing will come over there, right? But he said, well, if it comes that far, you should realize that the earth is a little bit round, right? Huh? So it will crash to the earth over there, okay? Sure, right? Huh? That stands to reason, right? Now he said, just keep going on. So here's your earth now, and here's your cannonball, and you're shooting it off. And then you do it like this, it's going to crash over there, a little bit further, it's going to crash over there, and a little bit further, and then we'll do this. Okay? It's still falling. Okay? So the moon is falling. So I can just use that same city law to describe all of this and get Kepler's ellipse. So I've unified terrestrial mechanics and celestial mechanics. There's only one thing. There's nothing else. This whole world, there's only one thing. It's called the force. Okay? It's brilliant. It's brilliant. The moon is falling. Everybody stopped laughing. You know? They thought it was a joke. Okay? Similarly here, we say, look, in economics, it's all about the economic force. There's only one thing that moves people is the economic force. Okay? That's just the assumption. Don't tell me about this, that, and the other, right? Huh? No. Per definition, everything is about the force. If you consume more, you do this, you do that, there must be an economic force acting on you. I don't care whether you think you're God, like celestial mechanic, or you're, you know, some, I don't know, warlord, huh? Okay? Whether you're an ecologist or a warlord, huh? Everybody has the same idea. The economic force applies to all of them. That's the idea. All right? Huh? Now, what does gravity do? Okay, the gravity force, gravitational decreases with the distance to the Earth, but if you're close enough to the Earth, it's approximately a constant, mg. All right? Huh? So this is going to cause you to just keep demanding more and more and more and more. So your needs are without, you know, a constant, right? So you can think of this as your needs. Huh? This is also called the standard gravitational constant, right? This acceleration. So I'll just call it the standard of need. This is just the needs that we all have in our everyday lives. All right? Huh? We need this, we need that. Everybody has the same. We all share that. Okay? That's how all objects share the same gravitational acceleration. Okay? You guys are cool with that? Huh? But what we do not share is our price elasticity. Well, I'm pointing to the price inelasticity, right? Huh? What objects do not share is their mass, right? So the force required to get this is going to change. That's the magic thing about gravity. When you think of it in the right way, it's not so magic. It's just that you need a force in order to get, any acceleration. And of course, it's going to be bigger for a larger object, for a heavy object, or a lighter object. But there was a lot of people, and still are today, is if you take a light object and a heavy object, I'll take a, they fall exactly at the same acceleration, right? Huh? Okay? These people will have, all people all have the same needs in this environment, all right? Huh? In fact, there's another famous quote by Adam Smith. I love these kind of guys, right? And it says the capacity of the no proportional density, and he will receive no more than that of the meanest person. By mean, he means lowest, right? The one who has the least, okay? Huh? So he said, whether you're a big landlord or the biggest president, your stomach is the needs of your stomach are going to be the same, right? Huh? Huh? But his desires, the desires, which is that force, can be immense if you are a big guy, right? Huh? So although your needs are the same, your desires can be immense. So you see that this quotes can be fit into this kind of thing. So this is an example of a force that is a force field, okay? So it's everyone. Everybody all at the same time feels there's hunger, and it's approximately the same for everybody, okay? Right? Huh? And no amount of desire, you can increase your desires, but that's not going to, this thing remains constant. Huh? It's just that if you're a big guy, you can effectuate a higher price. You can bid much faster. You can bid up much faster, right? Because this is the rate of change of the price, and you can just start bidding this thing up, and you'll get it. You'll get the resource, okay? Huh? Or you'll get the goods. It's not a resource, okay?
So the mass is how rich you are, basically.
Yeah, it's your price inelasticity, right? So if you look at a demand and supply graph, it's the slope. Okay? Now, if you're rich, maybe your slope is going to be very different, right? Huh? That's the implication. But really, I was speaking very slowly. It's just what it is. Huh? Okay? Huh? All right? Huh? So the flat of this thing is the higher the mass, right? Huh? So if you're already rich, probably you'll be willing to pay, but it's not the same. It really is not the same. I just make this leap because of, Okay? Huh? This is one of the good things. I like your question because it forces me to force you to go back to the definition instead of imagining something, right? You see? Whereas Smith, he didn't have this Newtonian infrastructure, so he knows all these things, but we would say the desires of the price inelastic agent bears no proportion to his needs, right? Well, the no proportion means that this proportionality constant can change. That's what it means. There's no standard proportion, right? Huh? That's how you should read it. Okay? All right? Peter, I see you nodding. Are you looking at something else or are you agreeing with this? Huh?
I'm also writing it down.
Yeah. Okay. Yes, so that's for clarification. Always follow the definitions, right? Huh? We've laid everything down, then follow it. And here, what we do is we take an economist and we just kind of decipher it, right? Huh? Okay? And then rewrite it, the intuition. Okay? So this is the first example of the force law. This is the gravitational law. So it's a constant, but it's a different constant desire for everybody, right? So the thing that's universally constant, that's the standard of the needs, and that's set by nature or society, where we say every person has a right to so many slices of bread and so many slices of cheese, I don't know what. You know, that's the standard of needs, right? That you can set to be constant for everybody, right? Huh? Whether it's a prison population or whatever. Everybody has the same standard, right? And then, and everybody, to find equilibrium, they all have to adjust their desires, all right? Given the price inelasticity, okay? All right. So this was the simplest one, we will hardly use it. I'll move to two other ones, and which we'll use all the time, okay? But the simple one is good to get going, you know? You can see it just allows you to, you know, to practice your... I'll just open up this. It's one thing formulating all the definitions and laws, it's quite another thing to be able to fluently apply it, you know? It's a lot of work that goes in there. All right, I'll start this one also with a quote from Adam Smith. If the commodity be scarce, the price is raised. It's terrible. I have this new AI-based grammar checker, Grammarly or whatever it is, and it hates every quote written by somebody historic. Everything Smith is written or Marshall or Einstein or everything, it gets totally upset about. You know, and I have to tell it to shut up or something. Anyway, that's a modern problem right here, right? So you get this dumb thing that you're not getting that these are historic. So now it is scarce. You should rewrite it like the price is raised when the huh? All right, so yeah, we can already see what's going on. The price is raised. So we got the P dot, right? Okay. And here we have something else, scarcity, right? Now, where does the P dot come from? Where does the price change come from? Huh? An economic force, right? So there must be some force of scarcity here that equals that, right? Okay? Now, what is this force of scarcity going to be a function of? Is it going to be constant? No, because when things are not scarce, right? Obviously, that force of scarcity, the price is not being raised. All right? Okay? So it's got to be. So how do you measure whether something is scarce or abundant? You know? Well, what about your at home when you want to know whether apples are scarce or abundant? What do? You go look in the closet and you see how many apples you have, right? So what do? I'm going to look at my stock and see if they're scarce or not, right? Okay. And depending on the stock amount I have, right, I'm gonna, okay. So you see, this is a one that is not a constant, and is a one that depends on the balance of apples I see in my my pantry. All right. Okay. Now suppose I make myself a life a little easier, and take the first thing that comes to mind that is not trivial, like not depending on Q, then I would take a linear function like this, right? Huh? Let's just get going. Maybe it's longer, you know, but then that will be the first term in the Taylor series or something, so it's okay. Huh? So at least for small variations, this will work, all right? Now, do you guys recognize this thing here? Of course you do, right? That's just a string law, okay? So I drew it here, the string, right? This is a spring that looks like this. Suppose here is the, this is how much has been stretched. Suppose here's the zero level, here after zero. And here I stretch it out to be long, right? This is long. And if I push it in, it will be shortened, right? Now, if I stretch it out, what is that force going to do? Well, we write that the force is equal to K times Q, but that's really a little bit sloppy, right? Because this Q is now positive. If this is zero, then it's positive. This is the zero position, right? And this is positive. And that force is acting the other way, right? Because it's pulling it back. All right? So there should be a minus sign, but that's all the action and reaction, and you have to keep our heads turned on, right? Okay? It's a restoring force, okay? That's okay. Just keep that in the back of your mind that we are very sloppy in these things as engineers, but then when we have to do the problems, we'll get them right, okay? And everybody writes a spring law like this, okay? All right? So this is actually the action force on the spring, and the reaction force from the spring is going the other way around, right? Okay? So don't get confused by that. So this is a very nice picture of your apples, right? So you can have some amount where you say, that you look at your closet and you have exactly the right amount in your storage, right? Where you feel comfortable with. At that point you realize my desires are zero to get more apples. I'm not going to go to the other tank, right? I just got a comfy amount here. I'm not going to tell the house youngster to go. All right? Or you can see too many and say, well, you know, we have to get rid of these things. Guys, apples on the menu tonight, because we got this enormous amount that we got for free, I don't know what, from the greengrocer who was dumping his apples on the menu for the next 3 days, all right? Or you don't have enough, and then you send somebody out to get some, all right? So this is what we say in finance especially, we call this position the neutral position. This we call a long position, and this we call a short position. And I've always wondered whether people must have had this in mind, you know? Like, it's so natural with a spring, okay? And when they made these kind of, you know, in finance, I was in finance for a long time, and we use all this mechanical language all the time, you know? And it just seems weird that it would, somehow deep inside us, we must all have a little economic engineer who comes up with this. Do you see this? I mean, it's just,
Shouldn't be the minus sign, because if you got 20 too much apples, then your desire is low.
Yeah, so if it's too much, this Q is bigger than zero, and this F has to counter it,
Yeah.
right? You see? So the spring itself will move, try to pull this way, and you have to pull it out. So you have to say, no, I'm going to force you to stock it, right? I don't care if you don't want it. I mean, if you don't stock these apples for me, I'm going to cancel your lease or something, right? Or I'm going to shoot you, right? Or I pay you to store them for me. But then you got to pay me for the inconvenience of having them. That's more usual. That's what people do. That's why you have to, if you store your goods at some storage place, you got to pay the person, right? Okay? He's not going to do that for free. I mean, he prefers to have nothing in there. He can cancel the whole building. all right? Huh? You see? So you have this action and reaction pair, right? So you have what, in finance you would call this a price action, and the other one would be the price reaction, right? Huh? So it's an exchange of value between the person who is incentivizing you to store it, huh? Probably somebody who doesn't want to run to the grocery store for every bite, and say, all right, I'm incentivized to do it because I have the cost of going to the grocery store and standing in line there, and I can use that time to study or work, and then you got a complicated economic mechanism that exactly explains why this spring is now extended, okay? You see? But it wants to be, if there's no forces, economic forces, the storage wants to be at a regular level. We did a project with Shell where they had these big containers, and they had some kind of level at which they wanted to keep it, because they didn't want to have the top over, and they didn't want to have too low, because then they couldn't fill their trucks, and the whole trick was to model that storage level, to model these forces so that everything would be balanced, okay? Now you have it in your application, right, with these credits, the amount of credits and debits, right, the money stored, that you have to define some level as being the neutral, that's not whether you don't feel you need more money on the account or less. So you have a comfortable amount of money on your checking account or whatever account you have. That's not necessarily zero, because you want to have the convenience of conducting transactions. And if you have too much, you don't get interest, blah, blah, blah. Okay? So here you are. So it's just a spring law. And now this is just, sometimes this is called the scarcity force is the reaction force, and the convenience is the action force, or the other way around. So, the action, one of them is the convenience and the other is the scarcity, right? The convenience is the opposite of scarcity, okay? And in future trading, you see this also. They have something called the convenience yield, okay? And that's, if you, I don't know if you guys know the future markets. Do you guys all know what a future is? Yeah? You don't know? You can say no.
No.
So you can buy things on the spot market, and it's just you get it now, right?
Yeah.
Or you can say, I'll buy oil, but I want it delivered to me in December, right? That's not the same thing as wanting it now, right? So there's a different price for December oil as there is for, what is it? 17th of October oil.
It's like a call. Or
No, it's not a call. A call is, you may not call it. This is an obligation. You see? You see the difference?
Yeah.
A call is an option.
yeah.
So when December comes around, I can say, I'm going to exercise the option or not. But if you have committed to buy December oil, you're going to get it at that price no matter what. That's your commitment. It's the same as committing to buy it now. It's not an option. You just went to the grocery store and you bought spot apples. You can't say it's an option, right? That's the same as the future. It's not an option. It's a commitment to buy that, right? Okay. So what would be the price of December oil compared to the price of oil, the spot oil, the price of oil now? Well, what you would think is that, I don't know, there's some price in the future, maybe what I expect oil to be worth, all this junk, right? No. Why is the answer no? Because there's something called spot future parity. That means that, suppose it's a weird number. Well, suppose it's a really high number, so it's $10 now and $1,000, now in December. Then one thing I can do is say, okay, they're bidding $1,000 for this oil that I can buy now. You know what I'll do? I'll just buy some oil now, put it in storage, and then sell it to this dude. At the same time, I'll sell it to the dude for $1,000, and I just sit back and relax, right? And then I made a profit of $990, right? Now, does that happen? No, of course not. So what would you do? what you would do is say, I'm going to price the December oil equal to the price today plus the cost of storing it. Okay? Right? Huh? And that cost is called the convenience yield. Right? Huh? Because you don't have a part of that cost is called the convenience yield. You also have insurance costs and all these other things, but there's an extra amount that you have to account for is the fact that this person in December doesn't have the convenience of being able to use the oil right now, right? Huh? And that thing, that extra piece of the price puzzle, that's called the convenience, all right? And that's the storage, right? The convenience coming from the storage. You understand? Huh? And that is the spring force. Now they use a yield, so they write the spring force as an exponential, and it's kind of gets complicated. We don't want to do that, okay? And I know why they do it because, well, they don't have economic engineering, so they have to write everything as a yield, and it all becomes first order differential equations, and we are going to get second order differential equations. So there's something else going on here, and so there's an imaginary number, and all this. It gets a little bit more complicated. All right. Huh? And that's why it's called, that I call this the convenience. So it's the force of convenience, and it's the reaction force through the force of scarcity.
Is that the same as the cost of carry?
Cost of carry is everything together, right? Huh? So if you have, the carry is also the losses that you make, so the dissipated expenses, okay? So normally you would have like a spring, huh? Sure. But don't forget, there's also a little damper here, you know? So the cost of carry is actually, you know, these combined, okay? Because the carry is everything you need to bring it from here to December, and that has the convenience part that you're losing, plus all the expenses that you're making, all the, the interest on the money, all the stuff that's just lost forever. Because there are convenience you can get back. Okay, huh? But the other stuff is just gone, you know. Huh? All right, huh? The inflation, huh? Any transaction costs, huh? So you typically have to add for the total cost of carry, you have to add a damper. We'll get to that in those applications. All right, huh? So the cost of carry, they view it mostly as the carry minus the convenience. But I don't like this because this is a rate and times time. Yeah, this is maybe some Fourier or Laplace transform or something, you know, we'll get to it, you know. So we're going to be quite more sophisticated about it. But you have to separate, they get separated too, okay? You know that, right? You took a look at that, I think, huh? Yeah. Is that clear? Yeah, this is not a bad, you are allowed to say no, when I answer the question, does everybody know? You're supposed to say no, you're not like yes. Because even people who say yes, they probably benefited a lot from your question. Huh? Okay, clear? Huh? So convenience is scarcity, those springs, okay? All right, huh? So we're doing quite well here. So, maybe I should say, so there really is another thing that goes in, and you see there's this Q star that I bought, here I set it equal to 0, here's the 0, then in my picture I took this as a 0, it really doesn't matter, because you see the way mechanics work is, if you look at space, it actually is what we call homogeneous. I mean, there is no natural 0, right? It just isn't that, right? Huh? This could be 0, this could be 0. You take all space and just shift it. You can take all space and run it at a constant velocity. That's another crazy thing. You can't run it at a constant acceleration. Then you're going to find yourself being jerked back, right? Okay. So this Q0 has to come from somewhere. It's not part of space itself. It's the same as in economics. It's not part of the account balance itself, but there is a natural zero. So only in mechanics, only springs give you a natural zero, because every spring can give you 1 point, or maybe a circle if you're going to rotate this, but say on a line 1 point at which there's no force acting on it. Forces, you know what they are, because you'll feel them. You'll feel them, all right? So it will only have one level that is free of ones, force-free, all right? And that level that you can then use for the zero level there, all right? And this is how we calibrate this, okay? So it's some little extra structure that we need to add. A mass gives us a calibration for a zero level of the velocity, okay? And a spring gives us a calibration for a zero level of a position, all right? In electrical engineering, it's a little bit the other way around. You start, an inertial reference frame there is a zero level for the voltage. You know, that's the electrical ground, right? So you do it like this, and this is where the voltage is zero, Yeah, okay. Or the electrical potential. I always get confused how they do it, call this. All right, so they'll just call this the inertial reference frame, and then they don't really worry themselves about the charge, going there. We take the velocity as the inertial reference frame, all right? But either way, and then here, with the spring, then we do this, all right? In economics, you can do either, depending whether you use the mobility or the impedance analog, all right? Okay? See, you just look at this, analyze it, and you're done. All right. Let's go to our last one. Okay, now the friction, that's actually the hardest element, that's, Why? Because a mass is nice and simple, you just do Q, and the other one is, No, it feels like you've run out of options now, right? You see, if we go back to here, and really, this feels like the most symmetrical thing, right? You see how this thing depends on that, the integral of that. This guy, and then it's all over. And in a sense, it's true when you do Hamiltonian mechanics or Lagrangian mechanics. That's all they look at. Okay. So I don't know if you guys do that, Lagrangian and Hamiltonian stuff. You'll see they stop here. They don't have other force laws. Okay. They only have this potential force. Okay. So if you look at the Lagrangian, is this sign is that, this thing depends on P, that thing depends on the price of that. Okay? There's no thing depending on velocity or something like that, right? Okay? The Hamiltonian is the energy, This thing depends on P. With Lagrangian I did it wrong, it depends on P actually. Okay? This is the energy. Okay, and they don't have an energy with a damper, only power, right? Okay, but this is one of the strengths of Newtonian mechanics, why people could never get rid of it. Is because it knows how to deal with all these funky force laws. Okay. Newtonian mechanics can deal with this, I believe, gravity. But not this one, well, this one probably yes, but because it's just a constant. But they have Newton's gravity and they can deal with it. But then it stops, okay? So we plow on, and then we're gonna do a the friction force, all right? Now let's walk, friction, economic friction is quite popular nowadays, but in the days of Adam Smith, and they didn't really talk about it. There's something he talked about is the invisible hand that you've heard of. That is really due to friction in my eyes, but it's better to talk about that when we talk about power. So we'll postpone that. There's another thing Smith has was it's called the natural price. And, but that's also due to friction, but it's also related to, it's a composite effect, okay? So I want to talk about that later too. And so I couldn't find a good quote here, to say, all right, this is what it was. And instead, I just did it from a more, intuitive point of view here, okay? Now, you see here, I have these two things that I put here, and that's basically because you could use a damper in two ways. You can either connect it on the mat, right, like that, or you connect it to a spring. Like this. It's a slightly different look and feel, all right? Here it will depend on the momentum of the mass, okay? So here it will depend on the price, and here it will depend on the extension of the spring, which is the stock, okay? All right, so keep that in mind. The definitions, I'm not going to tell you that, but that's those are the two solutions that we have, all right? So let's first go through the most obvious one, which is this one, which is usually what we, which is the only one we look at. Okay? But for this presentation, I wanted to expand it a bit. This is also all that's in the paper, really. Okay? So for me, okay, if we look at a damper, I'm fast forwarding a little bit because I know you guys are engineers. But one thing that makes it different from a spring or a mass is that it doesn't store any energy, right? It just dissipates energy, okay? So it's it's something that's just intermediating the force, right? So if you have a mass and you connect it via a spring, then the spring can actually assume some of this energy and then release it again, right? While the force is while it's conducting that force to the, so the force is flowing through to the wall, but in doing so, it can actually take some of that energy, all right? So it's not, it's an intermediary for the momentum, but not for the energy, all right? But if I put a damper there, I can transmit the same force, but the energy somehow gets lost, okay? We say it gets dissipated. And actually, this thing gets hot and it just flows off. So there's a little bit of a distinction there, okay? A little bit. This is the most important distinction, okay? So economically, one of these dampers, they are not really agents in the same way that a storer or a demander is, right? They're more like an intermediary to connect some real agent to a market, okay? These are two agents. This is another agent. I call this a market just because the demand is constant, okay? And this is you. And you can be connected, you can demand more and supply more, and you're connected through this agent, okay? And he handles that, okay? And what he does is he looks at your velocity, right? That's your flow. And you can also think that as the throughput, right? That's how much you're eating all the time. And he needs to be incentivized to, communicate that to the market, But in order to do that, he's going to charge you some based on the throughput. Okay? Huh? All right? And that charge is a constant. Okay? If I write it like this, you know that V is P divided by M. Huh? Okay? And gamma I'm going to divide as B divided by M, so that's just the damping rate, right? Huh? This is just the relation between momentum. Then I can write it like this. This thing is units of 1 divided by time, right? Like day or something, right? Huh? So what does that mean? This force is sort of a weird derivative where I look at a certain rate of the price. So I'm taking a cut of the price per unit of time to do this. You see that? Huh? All right. So I'm asking you a daily percentage of the value transacted in order to flow through these goods. Okay. So in the impedance analogy, this flow through is a little bit more clear because you have this inductor, then the velocity will really be the throughput, right? And this charge is exactly the voltage that is over this inductor. Okay? All right? So this is something you could call a shipper or a broker. The shipper is not storing your goods. Okay? He's also not creating demand for the goods. Okay? So he doesn't really have a price for the goods at all. He's not interested in the goods that he's shipping. Okay? Has no price for it, he has no demand for it. The shipper also is not going to store them for you. That's the last thing he wants, right? He just wants to drop them off at the location. He gets really upset that the location is closed and he can't make his drop off or pickup. Okay? So he is a true intermediary, right? He's just shipping it. Same as a broker, like a real estate broker or whatever broker. You know? He's not interested in a bank is a little different. They'll hold on to your money to charge interest, but they shouldn't, right? But a true broker, when he does your house, he's not going to live in it for a few days by himself before he gives it back to you. He gives it to the seller. Only banks do this with your money, all right, when they do a wire transfer, all right? He's just passing it on between the buyer and the seller, and he's charging you a price cut, you know? Okay? So that's one way, that's the way you can interpret this damper. Okay? So if I put a math here, you would see that in the math has a certain momentum, that's the price. You would see the effect is that this damper would reduce this momentum, you know, in time of this. We'll get to the exact equation, but you know this. Okay? All right? And the lower is okay? So in the end, your demand will equal the market demand. So your excess demand will be reduced by the intermediary. All right, so it will allow you to trade with the market, and in that way, all the prices will equalize, or the demand will equalize. I'm sorry. Okay. All right. There's another way to do this. And this is really hard to draw in a mechanical system because it's really hard to draw parallel systems with masses. So I'm going to draw this electrically. So here the situation is a little different. Here you have a capacitor, so that's a spring, that's a storage. And I put the resistor in parallel like that. Okay? Oh no, that's actually doable. I don't know why I made this. Why I got upset about that. You can just draw this, right? So this is just the series equivalent of that thing, right? This is the one that was hard to draw. This one you can do. No, this one's also easy to draw. I don't know what I'm doing. Doesn't matter. I'll do both ways. What's going to happen here? Well, say this is some storage, right, of your goods. Now, and suppose nothing is coming in. There's just some charge on this thing, right? And if this resistor wasn't here, then we'd maintain that charge forever, right? But if it is there, it's going to lose its charge, okay, until finally it's discharged, okay? Huh? You know this. So what would this mean electronically, economically? It means that there is some amount of goods here, right? They're just sitting there happy as all, huh? Okay. But over time, somebody is taking that out, right? It's getting lost or taken out as part of the payment or something, okay? Now, the higher the desirability, so the bigger this voltage, right here, the faster that goes, right? Huh? That's what this is saying. Huh? So the higher you make this, the bigger that flow for a constant, same damping constant, okay? So what it's saying is, if this is high, the goods are very desirable. So if you have goods in stores that are very desirable, the amount of waste, you know, through stealing or otherwise, I don't know how it can get lost. Also for payment in kind, right? So you say, I don't want any money, I'll give you some of these apples, right? But if the apples are very desirable, he may want a higher cut because he's storing very desirable goods. And it's okay? So here, you can see this more as the loss is due to the high desirability of the items. They're just less safe. Okay? And the losses here, this is then the flow through this damper is the amount of goods you're losing. All right? Huh? Okay? You can write it like this, that's more compared to that. So it's also sort of a cut, but it's what we call an in-kind. So rather than paying value, you pay, you get a flow equal to a percentage of the goods that are in storage. Okay? Huh? Of course, we can price all of this, you know, put a price in front of it, and then you'll get it all in dollars. But for now, just think of the physical thing going on. I see you looking with a question mark in your eyes.
Yeah. Yeah, I was wondering if we want to model a broker or intermediary, how could we sort of, because it doesn't store energy, and it sort of dissipates it.
Yeah.
So how could we like model its profits of the broker itself? Can we then model it as a damper, or do we need to make some sort of a mass in the damper?
Really what we need to do is go to the next section and figure out what energy is, right?
Yeah, yeah.
Okay, and then I can answer that. So it's a good question, but I don't want to answer it now. I agree that I jumped the gun a little bit. So I said, look, you guys know that it must be different, that it must be an intermediate based on this argument. But I was hoping I wouldn't get this question, right? Because it really wasn't fair, because you guys don't even know what energy is in economics and how I should answer that question. So we're going to postpone that to next week, okay? But I could try to do a little bit better, but I only have a few more minutes. But what was the question again? Let me answer.
So the broker so the price cut the broker takes gets dissipated.
Yes.
All those the particles. So he cannot use the energy. So he doesn't take, the broker itself doesn't make any money.
No, he does. It's just that what he does with that money is to dissipate it, right?
Yeah.
So that's what happens. So around this thing, you should see a big bath of water coolant or whatever. And his choice is to take that, and there's all kinds of agents in here, right? All kinds of oil particles or water particles. I don't know what to put in there. And they're all getting agitated. So what this guy's doing, he's buying an ice cream cone, and he's buying a chocolate bar, and he's doing all of that, right? Okay. And these are all really microeconomic effects that we throw in one big heap and just call it a damper, right? But at the micro level, you don't have any friction. You know, in quantum mechanics, there is no friction, right? In Lagrange mechanics, there's no friction, right? These are just average effects, right? And this damper, if you look at it closely, I mean, how does it look, right? There's a little plunger here, right? With a little hole in it, right? And then they have this big, fat oil bath around there. And then where does the energy go? Well, it goes into heating up. This thing gets hot, right? A mass doesn't get hot just because it's moving. But and a capacitor also doesn't get hot. You know, spring doesn't get hot. But the dampers, they get hot, okay? Because that's where the friction is. Huh? Okay?
So could you then also use a damper to model a pure consumer?
Yeah, but he has demand.
Uh,
So you'll have to get a mass for the demand part plus the damping for the consumption part.
Yeah.
You know, so a consumer is not someone who is just consuming because he's also demanding, right? So these consumers or producers, they're more complicated. So our elements are all like P is MV or F is KQ, you know, they just relate only two variables to each other. And in economics, you may have a consumer who has a price level and a storage and he is consuming, so he has all three, you know, it's just a more complicated system, okay? So I use this weird word demander, it doesn't really exist, it's just this idealized thing, right? But so it is in mechanics. There are no real masses. I mean, masses can get hot, right? But that's not what we imagine when we have a point particle, right? Huh? Springs can get hot too. Springs have mass, right? Huh? Springs also have friction in them. But we imagine these idealized things, and I'm just doing this, okay? And that's what I want you to do. Huh? So when you hear the word consumer, or when you hear the word mass, a real mass is something else than the mass we mean when we say, hey, there's a mass there, right? Huh? Okay? And that's the same with economic engineering, all right? Huh? So there's storage, there's demander, and then this handler or custodian, they're really idealized things. A real custodian, man, all kinds of crap going on, all right? Huh? Now, in the next week, I want to do all the energy stuff, and then all this can be clarified, you know? And I kind of cheated a bit, which I told myself, there's nothing to do, and I did it anyway. Because what you want to show is that you don't need the concept of energy to explain Newtonian mechanics, okay? It's just not needed. In fact, when you have Newtonian mechanics, you can define what energy is, okay? And you can do it the other way around, but that's called Hamiltonian mechanics, okay? And in fact, historically, that's how it went. So they then used Leibniz. He had another idea, and he had something with energy that was close to our idea of energy. But they didn't know how it related to momentum or all this stuff. They had this m times v, but they also had mv squared, you know. Huh? It was only with Newtonian mechanics that they realized there has to be a half here, and that this is equal to the integral of dp, you know. Huh? And then you're done, and then it works, okay? So this thing is Newtonian, this is Newtonian, and then you can, but that's for next week, okay? Huh? So I kind of regret using energy as a way to argue that this is an intermediary, but maybe I don't because, huh? All right, because it's less pure, huh? Okay? So here's where we are now, right? So we've covered everything. So these are the definitions, right? One definition and one law, right? These are the laws. There's only this guy. And these are the laws of motion. Huh? And these are the force laws. Huh? Okay? It's always unclear to me what's the difference between a law and a definition, but because this is not really a law either. It can be, how can it be 15 laws, right? But this is what we say, the spring law to this law to that law, right? Huh? Okay? All right? Okay. All right, I'll see you then next week.